Hello, everyone. My name is Chike Okonta, and today I'll be discussing scaling AI networks with Arangodb and Node Enterprise. By way of introduction, I hold a bachelor's degree in computer engineering and a master's in artificial intelligence. I currently work as a software developer for health partners here in the United States, and I also lead a machine learning research team at Marksfim. You've heard a lot of experts by now predict that within the next few years we would probably have machine learning models in everyone's homes. Recent advancements are certainly making this a reality. But I think the better question is what happens when we start connecting these models. Well, research in this area has essentially revealed that there are a couple key benefits. We have better control over hallucinations. We are able to leverage the power of a mixture of experts rather than relying on a single model to serve every purpose. And more importantly, I believe we will be able to reduce computational costs as well. Ultimately, we are able to design more reliable and robust systems. A prime example of applied AI networks is the research platform Penrose Care. It uses digital twins to deliver preventive care resources to both patients and providers. Initially, the platform depended on a single model to analyze patient data. However, it soon became clear that developing specialized models for distinct aspects of the patient's digital profile was actually more effective. The back end powering this innovative application is Node Enterprise. It's a platform that encapsulates machine learning models within nodes and it makes them accessible to end users through dynamic networks. These nodes have proven to be very useful in that they allow you to share your technology with other businesses. You have a primary node, which basically serves as the front end. You have a set of secondary nodes, which could be created by you and owned by you. But then the highlight is the inherited nodes. A great example here is the Evo 2 40B model, which is actually owned by ARC, but is made available through NVIDIA and is shared with other businesses, in this case, Penrose Care. So in this notebook, we are essentially going to make an attempt to visualize the exact same network you just saw. And so what we've done is we've pulled down the same data into this notebook. You can see the same primary, secondary, and inherited nodes in this graph. And what we've done is we've used Network X to upload that data to Arangodb. You can see the graph with the exact same nodes, the primary, the secondary, and the inherited node. The inherited node is somewhere in the middle there. It's the number 12, and it is shared by the primary node of the end user, and then number 11, which is the primary node of the third party. Great, so we have our data uploaded to Arangodb. We can now begin to use queries to get data from the database. We have a couple tools from LangChain to do this. The first is the text to AQL tool. The second is the query node instance tool. And what this does is it actually allows us to send queries and prompts to the node instances themselves. The third is the text to NX algorithm. And what this does is it allows us to use the cuGraph on this notebook to accelerate a lot of the processing. So for our first query, we try to find out how strongly connected the nodes in the graph are. So this is an attempt to basically analyze the connected components. And as you can see, the results show that the graph is actually strongly connected, consisting of exactly one connected component. So that's great. So now let's try to replicate the same prompt we had sent in NVIDIA. We would try to predict the next DNA sequence based on the input tokens we've just provided. And what the model just did, it was able to find the node instance capable of performing this task, which is the node 25. And then right after that, it sent the prompt with the sequences needed, and it was able to retrieve the exact result we needed. So the ability to integrate and share nodes is certainly beneficial. However, there are challenges, and the biggest one is the induced latency that has to be addressed. As you scale up the system, there's a lot of latency induced, and what we would try to do now is we would run a separate notebook that would essentially demonstrate how using Arangodb and the cuGraph through GPUs essentially helps address this challenge. So to do this, here's a much larger graph, right? So it's much more dense. And what we've done here is we've essentially uploaded that same graph to Arangodb. You don't need access to Node Enterprise to work with this notebook. It's all available through an open source data set we've provided. And all you have to do now is integrate that into the notebook. Most of the logic stays the same. We're using GPT 4.5 preview. And all you have to do now is run the application. The only difference now is there is also a Gradio interface provided at the end of the notebook. What we'll try to do now is see if, with all of these nodes present in this pretty massive network, can we replicate the same thing? Can we essentially reach out to the same node running an Evo 2 40B model and figure out the shortest path from my personal node, my primary node, all the way to that node with that model at its edge? As you can see, this is a pretty difficult task, so it had to sort of combine a couple tools to get the same result. But overall, it was successful. It was able to highlight that you can start from 74 all the way down to 823. Let's go ahead and confirm that that is the node we're looking for. Looks like it is. And it was able to complete this task much faster than it would have without a GPU.